In our last lesson, we talked about arithmetic sequences, and in those sequences you have a first term, which we use the variable a for, and then a common difference d. And what you do is, starting with the first term, you keep adding the common difference d to the previous term in order to get the next term. Today we'll be looking at geometric sequences where there is a common ratio, we use the variable r, that multiplies the previous term in order to get the next term. So for these sequences, we're going to determine the common ratio r. And remember, because it says common ratio, this number has to be the same throughout the whole sequence or else it's not geometric. One thing to keep in mind as well, the common ratio is multiplying, but it's not dividing. So we'll take a look at that. So for the first sequence, you can probably see just from inspection, to go from one term to the next, you're multiplying by 3. So 4 times 3 is 12. 12 times 3 is 36, 36 times 3 is 108, and so on. The common ratio would be 3. Now for the next sequence, 270 to 90, you might be able to figure out that visually we are dividing by 3. But we don't want division, we want multiplication. Now a little trick that you can use, very similar to what we did for arithmetic sequences, take the second term, 90, and then divide by the first term, which is 270. Now in this case, I would want that reduced. 90 over 270 actually reduces to 1 over 3. So in this case, we're multiplying by 1 over 3, and remember that is the same thing as dividing by 3. So our common ratio r is 1 over 3 for that one. Now for this one here, you can probably see visually that we're multiplying by 4, but what you'll notice is we're going from 5 to negative 20, so we're actually multiplying by negative 4. Now, taking negative 20 and again multiplying by negative 4, a negative times a negative gives you positive 80, and then 80 times negative 4 is negative 320. So the common ratio could be negative, and what you'll notice is that the numbers will alternate from positive to negative if that's the case. So now to develop a general formula or the general term, starting with the first term a, so term 1 is equal to a, or what I'm writing it as here is a times r to the power of 0. So remember that anything to the power of 0 is 1, so the r to the power of 0 in this case doesn't really affect the a value. It's still going to remain as a. Now there is a reason why I've done that, because now we can see a bit of a pattern. If I'm going to now figure out what term 2 is, I take a, the first term, and I'm multiplying it by r once, or that will be written as a times r to the power of 1. So now if I want to figure out term number 3, I would then take term number 2, the previous term, and multiply it by r again. Now term 2, remember, is a times r, so if you can imagine a times r here in the place of term 2, we're now multiplying it by r again, which will give me an exponent of 2 on r. So we're multiplying by r twice for term number 3. Similarly for term number 4, so taking term number 3, multiplying by r again. So because for term number 3 we've multiplied by r twice, we're multiplying by r again, so that gives us ar cubed. Now just like with the arithmetic sequences, we want to look for some sort of pattern between the term number and then in this case the exponent on r, our common ratio. So for term number 2 we had an exponent of 1. For term number 3 we have an exponent of 2, and for term number 4 we have an exponent of 3. So what you'll notice is that the exponent on r is 1 less than the term number. So that is the pattern that we can see there. And that gives us an equation that we can use for any of these geometric sequences, that for term number n, whatever n is, we can calculate that as a times r to the power of n minus 1, so 1 less than the term number. So we're going to determine the formula or the general term for the following geometric sequence, and then we'll use that formula to find the 12th term. So the sequence goes 6, negative 18, 54, negative 162. So first thing, I can identify what the first term is, and that's the a variable. So that first value is 6. Now r, the common ratio. So remember, what you can do is a little bit of extra work if you need to. If you take the second term and then divide by the first term, -3 in this case would be our common ratio. Now you have to just make sure that it does apply throughout the whole sequence. So you can double check on your calculators. Multiplying by -3 will in fact give us this sequence of numbers. So our formula for term number n would be 6 and then times r to the power of n minus 1. So that would be -3 to the power of n minus 1. There is our general formula. So now we can use that to find for term number 12, the 12th term, by substituting in that n is equal to 12. So I'm going to write for term number 12, remember that subscript, very, very small and aligned lower, is equal to 6 times -3 to the power of 12. Now, you can type that into your calculators, but just remember that the exponents have to be applied first before the multiplication. So that will give us an answer of 3,188,646, so quite a big number. And that's going to happen quite often with geometric sequences because we're multiplying to get our next term, so those numbers can get quite big. So that's how we put together the formula for a geometric sequence. And later on in class, we'll be looking at solving for the n variable or perhaps solving for the a variable as well.